Okay, so welcome back in this course of advanced manufacturing and process modeling. So we were discussing about die filling section, and we have started discussing about rheological behavior of the liquid melt, because it is of paramount importance to achieve complete filling of the die cavity and also to achieve uniform distribution of the microstructure as well as properties in the solidifying part. So here you can see what we have discussed earlier also, that we in rheology we basically, it is the science dedicated to study the viscous evolution of the fluid, in this case liquid melt, which is of paramount importance. So it is the measurement of shear viscosity with a single head in case of stress control experiments by rotational viscometer. So the sample, in this case the sample is loaded between two parallel plates when we are talking about parallel plate geometry with an exact gap h. So this is the gap h between parallel plates. So this is say plate 1 and this is the plate 2, and this is the gap between them. So single head rheometers can be set up for either controlled rate measurement, where a rotational speed is applied and the torque required to maintain the speed is also applied, or controlled stress measurement, where is torque is applied and the rotational speed is measured. So, as if you recall, I have discussed about the earlier class that the rotational viscometers can be defined as Serle type and Cotte type, and for in case of cup and bob geometry, but the viscometers can also be rotational and also parallel plate type, where it can also be rotational and also reciprocating. So there are several variants of them, but the end goal is basically the same, to evaluate the viscous evolution of the solidifying slurry. We are talking about liquid melt here because that is our subject of consideration. So we can see over here in this graph, which is plotted between shear stress tau and the shear rate, we can be defined as gamma dot is equal to nothing but du dy, which is the velocity gradient. So you can see, so these are different kind of fluid and how their shear stress and shear rate relationship. So based on that, it can be distinguished as Newtonian, where basically it is constant. So they are basically proportional to each other, and whereas in other case it is a case of shear thickening, that is dilatant fluid, where you can see with the increasing shear rate the shear stress value is increasing, and then this is a case of shear thinning, where you can see with the increasing shear rate basically shear stress is dropping and simultaneously its viscosity also drops. And then there is a case of Bingham plastic. So we are basically in case of solidifying liquid melt, we are basically focused on the kind of fluids. We are talking about the kind of fluids which are basically shear thinning. So here viscosity value starts dropping as and when we are increasing the shear rate. So this is the property that we are taking advantage of, and that is why we are, although during during die filling also, because the die is kept at, even if it is preheated, it is relatively cooler than the liquid melt, which is poured at a superheated or high superheat or low superheat condition. So as and when it is flowing through the intricate die cavity, through runner, ingate, and also runner extension. So that time there are chances of solid formation within that, and it happens in reality, and that is why then suddenly that the viscosity can go up. However, because the fluid is in motion and there is the shear rate which is generated, the shear because of the shear flow and the shear thinning nature of the solidifying liquid melt, is viscosity drops, and that is why it remains enough flowable and it is capable of filling the complex contoured component cavity, and thereby we can get the sound structural parts. So here shear thinning behavior is explained properly. So shear thinning behavior is the most commonly seen type of non-Newtonian behavior, which is called shear thinning, and also called pseudoplastic flow. So during shear thinning behavior, the viscosity of the fluid drops as the shear rate increases. So at a low enough shear rate fluids which exhibit shear thinning will have a constant viscosity. So this is the case of constant viscosity. Okay. So beyond this region, the moment you are increasing the shear rate, it start decreasing first gradually and then it is in a exponential manner. So, this is a region where the power law model is applicable, where there is a I mean catastrophic drop in the viscosity of the shear thinning fluid. Okay. But in the whole regime the cross model is applicable. That means, starting from the 0 shear viscosity, that is can be termed as eta 0 to I mean it is a highly shear thinning. Again there is another constant when it approaches, when even if you increase the shear rate further, the viscosity does not drop beyond that. So, for the whole I mean region of the curve, the cross model is applicable. So, at a critical point, a significant drop in viscosity we have discussed. So, why does the shear thinning behavior occur? So, you see it is nothing but the rearrangement of the molecules, fluid molecules, that causes the shear thinning behavior. And in case of solidifying liquid melt, so what happens, like for example, if you are taking an example of say aluminum copper alloy. So, so in this case, so from this liquid melt of aluminum copper alloy, the moment its temperature locally goes below liquidus temperature TL. So, the when T is basically I mean less than TL. So, in those liquefations, as we have discussed earlier about the nucleation mechanism of the solid I mean primary grains from the liquid melt. So, so these primary solids are emerged, and then I mean when we are applying the shear rate. So, then basically I mean it allows the these particles and also the fluid to glide past each other in a smoother manner, and suddenly this network which is getting developed between these solidifying particles, it gets broken, and then they become oriented in a distant manner like island, and it allows flow past them, and also these particles glide past each other in a smoother manner, and subsequently the viscosity drops. So, this is the reason in case of I mean solidifying melt, where we are seeing the shear thinning behavior. Okay. So, I mean so then we are moving into the thixotropy. So, thixotropy is basically nothing but a time dependent viscous evolution of the solidifying liquid melt. So, I mean it is the majority of the liquids which are showing shear thinning behavior is completely reversible, where with the shear liquid returning to its normal viscosity once the force is withdrawn. I mean the force, the shear force which is exerted to enable it to flow, it is withdrawn, it again behaves like a solid. So, this is called thixotropy. That means fluid at rest. For example, like I have expressed in the previous slide to this. Assume that this network is getting built, and when if you are keeping it at rest, it is showing like a solidifying mush, and it is a highly viscous matter at this moment, which is having very high viscosity, and the moment it is subjected to shear rate, I mean a significant shear rate, it becomes flowable and it behaves like liquid. So, this is the property of this fluid which is called thixotropy. So, because of this it behaves like solid when kept at rest, and it behaves like liquid when is under subjected to shear. So, so thixotropy is the result of the time dependent rearrangement of microstructures in case of solidifying melt or fluid molecules when there is no phase change is involved at the onset of the shear applied. So, shear thinning materials can be thixotropic, whereas thixotropic materials are inherently shear thinning. So, this is the basic concept of shear thinning and thixotropy. So, now we will again discuss a case study of rheology that has been done in our group, where we have studied the viscous evolution of a solidifying liquid melt within a rotational rheometer, more specifically the Sarle type rheometer, where I have already told you that in this case, in case of Sarle type rheometer, the rotational grooved bob is basically rotating, and the outer cup within which the bob rotates, that remains as stationary. and we basically keep the fluid in the annular space, for which we are basically measuring the viscous evolution. In this case, it is basically the solidifying liquid melt. Okay. So, the relation existing between applied torque capital T and the shear stress tau through the annular gap at an arbitrary radius from the axis of rotation. So, this you can assume as the axis of rotation, assume this is x bar. Okay. So, from there so we can estimate the shear stress at any radius from the axis of rotation, say assume here. So, this is where this is the radius r. So, then shear stress tau at this point we can determine from this expression, that is tau is equal to applied torque T by 2 pi r square L, where L. So, please correct it, where L is the length of the bob beneath the melt surface. The shear rate distribution present within the annular gap between the cup and the bob can be expressed as the below equation. So, this is the equation. So, this is equation 1. So, this is equation 2. So, where gamma dot is equal to 2 omega by r square. Omega is nothing but the rotational speed, angular speed of the bob, and capital small r ri is the inner dia and ro is the outer dia of the bob and cup. So, Ri is basically the the inner geometry dia from the radius from the axis of rotation. This is Ri. So, this is I have already drawn the axis of rotation. So, this is Ri, and this is the inner dia of the cup is basically the R0. So, we are basically interested in estimating the viscous evolution of the solidifying melt in this annular space between the rotating bob and the stationary cup. Okay. So, here this delta this gamma dot is equal to 2 omega by r square into r square minus r I square by r o square minus r I square. So, so I have already expressed what is the significance of r inner and r outer, and so and omega is the angular speed of the bob. So, up to this it is so we have estimated the expression of the shear stress, we have estimated the expression for shear rate, and the equation of viscosity in case of Newtonian fluid, that is shear stress divided by shear rate. That means as we know, tau by du by dy is equal to mu, that is the viscosity in case of Newtonian fluids. So, which is this equation is basically called the Margulis equation. This does not hold good in the present case, because we are talking about a pseudoplastic fluid, that means the solidifying liquid melt. So, the expression for viscosity in case of semi-solid slurry is a complex function of temperature. So, this is the expression. So, you can see it is a function of temperature T, and then this is the Cl, that is the liquid fraction, it is the function of the shear rate, it is the function of history effect, and it is also the function of cooling rate, and so on. So, however, it is and also it is a function of shear time Ts. So, however, in reality we generally neglect cooling and history effect, and grossly we express the viscosity as a function of shear rate and temperature or solid fraction Fs. So, they are commensurate, because temperature and solid fraction, it is basically in case of a solidifying liquid melt, they are they are dependent over each other. So, if you can if I can draw the typical expression for Fs versus T. So, as the temperature T increases, Fs solid fraction decreases. So, so we can extrapolate the value of solid fraction from the value of temperature of a liquid melt. So, that is why so there cannot be two functions, they are basically one function only. So, generally we express viscosity of the solidifying liquid melt as the function of shear rate and temperature. Okay. So, in this case in our case study, so we have basically used the Oswald D. Wale power law model to construct our rheology model in case of a popular aluminum silicon magnesium alloy, which can be expressed as aluminum 7 silicon 0.3 Mg alloy, which is a very popular cast alloy, I mean die castable alloy, which are widely used in for high pressure die casting and development of several automotive and I mean aerospace and several other parts for several other industries. So, in case of Ostwald-Dewale power law model, so it predicts shear rate as a function of solid fraction and temperature, and in case of Carew model, it is also based on shear thinning behavior. So, as I told you that we have taken the Ostwald-Dewale power law model, and also we have basically mixed, I mean combining Ostwald-D power law model and also the I mean Arrhenius model, from where we can write is that A is equal to B by T. So, this is basically the expression for the viscosity in case of Arrhenius model. So, combining both of them, we basically developed a rheology model which is capable of explaining the viscous evolution of this aluminum 7 silicon 0.3 magnesium alloy during I mean its solidification. Okay. So, the case study objectives is develop a comprehensive rheological model which describes the effects of solid fraction, aka temperature. So, as I told you several times, there can be extrapolated between them, and the shear rate variation on slurry viscosity using a single function. So, the methodology, the model used on the Ostwald-Dewale power law model and the Arrhenius model. So, they are combined to each other, and then we arrived at this I mean model. So, power law expression, the shear stress and shear strain rate are related through Ostwald-Dewale power law expression as given below. So, shear stress tau and shear strain rate I mean omega I mean delta dot I mean lambda dot are related by the Ostwald-Dewale power law model as such. So, here shear stress tau is equal to C the constant into I mean shear rate gamma dot to the power n, where C is the power law constant and n is the shear rate exponent. Okay. And then Newtonian viscosity relation is what, where I mean as we know that tau is equal to mu du dy, I mean shear rate. So, here we have expressed shear rate as gamma dot. So, then viscosity how we can get? We can get by dividing shear stress by shear rate. So, then what we know from here? So, tau is equal to C gamma dot to the power n divided by gamma. So, that means we are getting C gamma to the power n minus 1. So, we have termed at m. So, that means C gamma dot to the power m. So, this is basically the expression for the I mean viscosity, that is what is considered in this model. It is shown over here, and here m is equal to n minus 1. So, n is the power law index. So, in case of this particular this alloy, this aluminum 7 silicon 0.3 magnesium alloy, it is found that it is highly shear thinning, and it is found that a value of this exponent n is 0. So, then what it becomes? So, then viscosity expression becomes C, that is function of T gamma to the power gamma dot to the power minus 1, that which shows it is highly shear thinning. Okay. So, this is a typical I mean viscosity versus shear rate curve for different temperature I mean and corresponding solid fractions. So, I mean where you can see that for it is shown for 3 different temperature, that is 605 degree centigrade, 590 degree centigrade and 580 degree centigrade. That means, so with the decreasing temperature we are basically increasing solid content within the solidifying this aluminum 7 silicon 0.3 magnesium alloy. And you can see that with the increasing solid content that the viscosity is increasing. So, as you can see that in case of 580 degree centigrade, the viscosity evolution curve slopes higher than the other two curves which are plotted for 605 and 590 degree centigrade, where 605 is the minimum because of the minimum solid content present within the solidifying melt in this case. Okay. So, what is the final form of the viscosity model? As we know that mu is equal to C, that is the constant, power law constant, I mean shear rate to the power n minus 1, and we have also evaluated the exponent I mean shear exponent as n is equal to 0. So, then C t gamma to the power minus 1, but please recall that we have expressed that we have established combining the both Arrhenius and power law model. So, from Arrhenius model we know that So we are basically putting that expression over here. So if we express C is equal to A I mean e to the power b by t gamma to the power minus 1. So, then from here, so this is basically the constants which are evaluated from the rotational viscometry using a Sarle type rheometer. So, here the value of A is this one and the value of b to the power b by t. So, value of b is this one. So, this is b, this is a, and then this is to the power gamma dot to the power minus 1. So, this is the resultant viscosity model that we have developed, and this is basically used subsequently for simulating the die filling behavior of the a high pressure die cast component like for example, knuckle housing, that we will be discussing next in this section. So, here you can see, so these are some salient outcomes of this study on rheological behavior of this alloy, aluminum 7 silicon 0.3 magnesium alloy. So, in case of isothermal rheological test conducted for 3 different temperature, that is 605, 590, 580, and corresponding solid fractions are this. So this is already explained to you in the earlier slide how increasing solid fraction impacts viscous evolution of the solidifying melt, and the observations for individual temperatures, like in case of 605 there is a sudden decrease. So, flow curve shows a drop in viscosity. You can see from here. So, this is the case of 605 degree centigrade, that means with the minimum solid fraction. So, you can see there is a sudden change of slope over that region, that means basically it is happening due to the breakage of the solid networks at this shear rate that has been explained to you before. So, this is basically happening due to microstructural changes that is happening within the solidifying melt with the increasing shear force or the shear rate. So, this sudden decrease indicates stress build up within the semi solid matrix during shear in a Sarle type rheometer. Trend reversal occurs around 700 second inverse shear rate. So, responsible for the change in slope of the viscosity flow curve, that again it is explained to you, it is happens because of the microstructural restructuring, microstructural changes that happens at the onset of shear force exerted by the rotational geometry, that means the inner bob in case of a Sarle type rheometer, and in case of lower temperature stress reversal occurs at a later stage. Why? Because in case of lower temperature the solid content within the melt is higher. So, that means the solid network which is growing within the solidifying melt is even much more stronger. So, that is why it needs even higher shear rate to break this network and to disintegrate this network in the form of small islands or particles. So, that the fluid flow so the liquid melt is enable these solid particles to glide past each other, and also to transfer the shear so that the flowability of the slurry increases. So, that is why viscosity drop at the onset of increasing shear happens at a later stage. Okay. So, the stress reversal later stage happens due to higher solid content and stronger bonding between evolving alpha aluminum grains. Okay. So, these are the salient points. So, rheology, definition and characteristics of SSM processing, definition, processing of alloys between their solidus and liquidus temperature, and key features. SSM slurries behave like a solid at rest and flow like a liquid under shear, exhibit thixotropic behavior, meaning they show shear thinning. Viscosity decreases with applied stress. Importance, it enables processing methods such as Rheo-casting and thixo-casting. So, as you may recall that I have discussed during when we have discussed the casting solidification section of this course, where we have discussed that Rheo-casting is nothing but generating semi-solid slurry directly from liquid melt and then casting it in semi-solid state, and thixo-casting is the otherwise, where we are generating semi-solid from the solid ingots and then at that state we are casting to achieve the desired component geometry. So, this viscous evolution of the slurry, that knowledge is of paramount importance to achieve success in both these semi-solid casting processes. So, the rheological properties of SSM slurries, what are they? That is flow behavior, it exhibits pseudoplastic non-Newtonian flow characteristics, and it shows dependence over temperature, stress history, and also I mean cooling rate, and also microstructure, so on. Application: rheological studies are crucial for understanding and optimizing Rheo-casting and thixocasting as stated before. And so, advantages of SSM processing also discussed to you earlier, that it offers significantly improved mechanical properties, higher structural integrity, and also I mean it enables casting of thin sections. So, I mean, so you can see that they are connected to each other. I mean the rheological evolution, and also die design for I mean semi solid casting, and of course, rheology is equally important for the conventional liquidous casting also, because as I told you that I mean when the superheated melt flows within the die cavity and at pockets at locations, solid formation already starts. So, it becomes important to investigate the viscous evolution of the solidifying melt, so that we can achieve the I mean solidified parts free from defects. So, here as we have discussed about this aluminum 7 silicon 0.3 magnesium alloy, which is commercially known as A356. So, why it is chosen for this particular case study is because it has got a wide difference between the TL and TS. So, this is typically the I mean phase diagram of this particular alloy. So, you can understand from here that I mean that it is basically I mean having a greater I mean temperature zone. So, this is basically the TL, and this is basically the I mean eutectic temperature, also termed as TS if we are approximate it as binary. So, in this case sorry, this will not be the case, please do not consider this. So, this is the temperature, and this is the I mean so this is where the alpha particles nucleated first. So, this is the superheated liquid state, and here it is the mushy region, that is alpha plus liquid, and beyond this it is the solidified particle. So, so here because of this larger window I mean larger gap between TL and TS. So, in this case the TL is around 615 degree centigrade, and the solidus is somewhere around 555 degree centigrade. So, you can understand here that there is a gap of I mean 60 degree. So, there is a gap of 60 degree almost. So, that is because of that I mean we can basically process it using semi solid processing by variety of techniques like using cooling slope, or using I mean electromagnetic steering or mechanical steering, and so on. And that is why it is very much useful for Rheo-casting, and also it offers excellent castability, good weldability, pressure tightness, high strength to weight ratio, and good resistance to corrosion. So, because of these attributes it has got wide applicability in automotive and aircraft engine components. And examples of popular casting alloys are like other than A356, there are A357 and A380. These are also the die castable aluminum alloys which are widely used. And so, even in case of A380 there is a significant presence of iron content within the I mean aluminum alloy, which is also useful for enhancing the die life of the I mean this high pressure die casting mold. So, these are the attributes which make it I mean useful for die casting application. So, significance: these alloys form the basis for semi solid manufacturing due to their favorable properties. So, so after this we will basically discuss the I mean the die filling attribute of a high pressure during semi solid die casting of this A356 alloy. So, for that it is important to understand its I mean heat I mean its I mean the different temperatures. So, for example, this is basically its liquidus temperature, this is basically its eutectic temperature, and this is its solidus temperature. So, all these three temperatures are of very much importance to decide and also to optimize the process conditions of I mean this semi solid die casting processes. and even if we do the same process in gravity, that means if we do the Rheo gravity die casting process, there also these temperatures are very much essential to decide on the process window. So, so this is basically the TL liquidus temperature, this is the solidus temperature, and this is the TE, the eutectic temperature. So, we generally need to be in between the TL and TE, that is the eutectic temperature. So, we should not go below eutectic temperature, even if theoretically it is possible to process the semi-solid slurries between TL and TS. However, this gap should be restricted between TE and TL, otherwise it becomes the solid network becomes so rigid that flowability significantly drops, viscosity increases so high that feeding I mean becomes very difficult, and that causes defect formation. So, basically this is the window between eutectic and the liquidus temperature. There we need to restrict, and accordingly we have done the same in this case study also. And so, this is basically the solid fraction versus temperature curve for the same A356 alloy. So, you can see over here that up to a certain temperature drop there is an increase in solid fraction gradually, and beyond that I mean beyond that you can see that close to the eutectic temperature and beyond there is a catastrophic increase. So, we have to basically restrict ourselves to I mean up to this region. So, we need to play between this region of temperature. So, I mean up to in between this region of temperature, that is 615 and 615 degree centigrade and 577 degree centigrade for this particular alloy, and this is true for all other aluminum magnesium alloys also. So, we need to restrict between these two temperature, liquidus and eutectic, and so we will now discuss about the semi solid die filling in case of Rheo-casting, considering knuckle housing of automobile as a prototype component. However, we will discuss in detail about the same in the subsequent class. So, we are basically stopping for this class here, and we will certainly continue from here on. Thank you.